Hello, everybody. So it is finally happening today. Today, we will discover a solution to our endogeneity and simultaneity problem. So I'm going to get right into it because today's lecture has a lot of stuff in it. And it's an important one. And I encourage, this is a great one. Like the last lecture with generalized least squares, this is a great one to think about projects around because this is some of the stuff that is very unique to the practice of econometrics. And I think some of the real value you can get out of this class relative to some of your other classes. So first, I'm going to give you a bigger, more bold sort of background to endogeneity because we've mostly looked at specific examples like simultaneity in the supply and demand system, but there's other examples where this can show up. So endogeneity, so we use the term endogeneity to describe this situation where the covariance between our independent variables and the population error terms is not equal to zero. So something is causing correlation between our independent variables and our population error terms. Now we saw already that this is difficult to test because by the nature of ordinary least squares regression, where we choose our parameters by minimizing the sum of squared errors, that always leads the covariance of our independent variables and the sample errors or residuals, if I had an E right here, that's always equal to zero. So we can't just look in the sample and test this because that will be forced to zero by the mathematics of ordinary least squares. The existence of endogeneity is often difficult to test for the reason I just mentioned. The fact that endogeneity is difficult to test statistically and often appears in human systems has led economists, because of course economics is a lot about human systems, and we can come up with a lot of cases where we might expect this endogeneity issue to show up in those systems. So that's led economists to develop the tools and the theory with which we confront endogeneity issues. This focus on is one of the defining characteristics of econometrics relative to other fields of data science. And so if we have reason to believe that independent variables are correlated with the error term as described by the covariance of the x values and the epsilon being non-zero, so if we have reason to believe that, maybe a theoretical reason to believe that, then we refer to those specific independent variables as endogenous variables or endogenous regressors. Independent variables that we do not believe violate this assumption, we can refer to as exogenous variables. Endogenous basically means from the inside. So something's happening inside the system that leads to correlation between the error terms and the x values. Exogeneity means from the outside, so there's no real way for that codependence to exist within the system. So that's where those terms come from. From the inside, endogeneity, that's the one that's going to be the issue. Exogeneity from the outside. And this is why sort of statistics done on laboratory experiments is if a physicist or a chemist is doing a laboratory experiment, then they don't really have to worry about this because the variables that they tweak in order to test the different theories are generally from the outside. They change the conditions of the laboratory from the outside. So this is rarely an issue in those types of scientific studies. It becomes a huge issue when we go to observational data, which is very common in economics and tons of applications in data science. So I'm going to go through some more examples of endogeneity problems. We've already seen simultaneity, and we've actually seen some of these show up. Again, these are not like mutually exclusive problems. So I'm going to give you different examples of the terms people use for these problems. Mathematically, they might be very similar problems, but oftentimes we like the stories around these problems because that's where our intuition comes from. Because again, this is not testable. This is something we've seen. If we simulate data, we can see it. But in general, we're going to go collect data from the real world that's not simulated. So we can't really see this problem. We only might have a theoretical reason to believe that this problem exists. Now, once we go through some of the methods that we fix the problem, then we can sort of compare results from the different methods. And if we got very similar results from the different methods, like we apply ordinary least squares, and then we apply one of the methods that helps fix endogeneity for us. If we observed very similar results across those two models, then maybe that tells us it doesn't even tell us that we don't have an endogeneity issue. It tells us that that endogeneity issue is not leading to bias. So we could kind of say that once we apply methods, if we are confident that our method would have solved the endogeneity problem. So let's go through a couple cases, a couple I've mentioned at least briefly before. So the first I'm going to mention is omitted variables. So consider the population regression model, natural log gasoline consumption. So we're going to model the natural log of gasoline production as a intercept plus a population slow coefficient times the price of gasoline. So this is looking like either a supply or demand equation. And then maybe also gasoline consumption depends on income. So we can imagine this being the true population model. This is probably overly simplified, but for example, maybe this is the true importance. So gasoline consumption is totally determined by price and income. So we probably have an endogeneity problem from simultaneity like we've seen before, but right now we're going to focus on the potential of having omitted variables. So suppose then this is the true model, but then we run this model right here. Notice that this model is the same model, but without income in it. And now I'm going to change the error term to omega, because now if this is the true model and we write down this model, then that means that omega equals beta 2 ln income plus epsilon, because that's what we're leaving out. So again, if this is the truth, but then we assume this model, then we're leaving out this part of the truth, and then that's ending up just all in the error term. Okay. So now maybe the price of gasoline is correlated in income, like places like maybe in San Francisco where income is relatively higher, gasoline is also relatively higher, and places where income is relatively lower, like rural Alabama, gasoline prices also relatively lower. That would mean that the natural log of income and the natural log of price are correlated. And then we can see immediately if that's the case, then the natural log of price and omega, the error term in this regression, this population assumed regression, are not zero. So make sure you understand that if we replace this all with just omega, and if natural log of price and natural log of income are correlated, then in this regression, natural log of price is correlated with omega. And so omitting a variable that A matters and B is also correlated with other independent variables leads to an endogeneity problem. So that's a very simple case of an endogeneity problem. So intuitively, if the omitted variable is correlated with both the dependent variable, consumption, and other independent variables like price in this case, then we will have biased estimates. We will get the wrong guess of beta 1 when our beta hat or B1 will be biased theoretically by this issue. We can intuitively predict the direction of this bias in many cases. So that's one important reason to understand omitted variable bias. You might know that you have a population regression like this, but for some reason, some of the variables are impossible to collect. So you just have to accept that you will have omitted variables. Well, what's nice, if you know the direction of some of these, you might be able to reason out the direction of that bias at least. So that can be very useful because maybe you understand you have the wrong coefficient, but at least you also understand that it's too low or too high. So an example I've brought up before, but I would like you to think through on your own again. What if we ran a regression of home price with the dependent variable and number of bedrooms as the independent variable, but we did not control for the size of house? in what direction will the coefficient on number of bedrooms be biased by omitting the size of house variable? So I've given that example today before. I'd like you to think through it the same way we just thought through this logic. You could write down this true population equation with the number of bedrooms and house price, write one down with only number of bedrooms with a different air term, which will now have square footage in it. What is that going to lead in terms of like your estimate of beta 1? Why will it be wrong? What direction? That's definitely worth thinking about. Now, a big one that comes up that can often be related to omitted variables is endogenous treatment effects. So consider an attempt to estimate the treatment effect of going to an elite college, for example, where X is the matrix of control variables and an intercept, and T is a categorical variable, 0 or 1, equal to 1 if an individual attended an elite college, and 0 otherwise. Delta is referred to as the population treatment effect. That's what we want to estimate, the effect of going to an elite college. However, some observed or even unmeasurable determinants that impact earnings. Why? Because our earnings are going to be our outcome variable of interest, the natural log of earnings. So, for example, ambition, an individual's ambition is probably correlated with earnings, but it's also correlated with their ability to attend elite college. So that's exactly like an omitted variable price bias, and it's going to be difficult in this case to actually just go collect this variable called ambition, and that's why it's its own category, because oftentimes this omitted variable problem shows up in ways that are not easy to collect data on, like ambition. So this fact often motivates what are called natural experiments for these treatment effect type situations. And so individuals are randomly selected into the treatment group among other methods. An example of that is a John Snow, which is really where these randomized control trials and things like what are called difference in differences originally came from, which we'll talk about a little bit more in the future. But this John Snow cholera experiment in London in the 19th century is very interesting to think about. It's very old, but it will show you the value of some critical reasoning around data that started a very long time ago. So I encourage you to look at that John Snow cholera experiment. It's very interesting because basically the authorities were incorrect about the nature of cholera because of these types of issues. And they had the wrong theory about where cholera is coming from. And John Snow sort of proved that it was coming somehow from the water system and not from air, basically. So, of course, we've already looked into simultaneous equations like demand and supply quite a bit. So consider estimating the parameters of supply and demand, which you've already considered several times. If you only collected price and quantity data, that would be an issue. So I won't go into the details of that one because you've had some experience with that one already. Another place this shows up is in panel data regressions. So panel data, and specifically dynamic panel data models. So panel data means we have variation across space and time. So maybe I'm looking at inflation rates in every state in the United States in every quarter of the year. So I'm getting 50, just assume I'm not looking at DC, I'm getting 50 times 4, 200 observations per year, because at each quarter I'm taking a cross section of inflation. So at each quarter I'm getting 50 new observations of inflation. Then the next quarter I get 50. So the variation in my sample happens at any given time. I have different inflation rates across states. And then at any given time, I have different inflation rates even within a state. So the variation in my sample is coming from both places, space and time. That's a good type of data to have because it has a lot of information in it. However, oftentimes it's useful, particularly in something like inflation. We expect inflation in the current period to be related to inflation in the last period. Inflation doesn't jump around from like positive 10% to negative 10%, then back to positive. It doesn't jump around like that. If inflation last time was 4.5%, it's probably going to be pretty close to 4.5% this time too. Maybe a little bit up, a little bit down. Now, with models like that, so if this is inflation, we like to include lagged inflation because that's a good predictor of current inflation. In state I and time t, state I's inflation at quarter t minus one, so 3 months ago, might be a great prediction of that. Now, of course, there's other variables that also might matter for inflation in that state, like how fast the economy is growing in that state, what's happening to the population in that state, things like that. Now, in a model like this, oftentimes we just have our regular error term, epsilon IT, but then we might have a unique error term per state because maybe there's some individual component to the error term itself. Because California maybe experiences different sort of types of error terms in terms of inflation than other states. And that's, we're going to assume when we write this model down that that part is time invariant. We can't really write that it's IT2 because then it's not really different than epsilon. So we're being explicit, like we think part of this error term is time invariant and related to the state or the individual or whatever that spatial component to our model is, the part that doesn't vary with time. If we make that assumption, then we can write the error term this way to decompose and just to express that we think part of this error term is a standard, comes from regular observation, but part of it is associated with what state we're in. So now the unobserved heterogeneity represented by UI, so unobserved differences across states, and those impact the outcome variable, inflation in my example, in every single period. A very large UI will lead to a larger YIT minus one. That's an independent variable. So if this is large, this being large leads to this being large, that sounds a lot like correlation. And so there we go. We have the covariance of YIT minus one, the lagged independent variable, which is an independent variable, is now correlated with this error term structure. So that leads to an endogeneity problem. And there's many. This is a very big issue in economics empirical studies and many other empirical studies because with big data, we have more and more panel data sets and more demand for these types of dynamic panel data models. So there's a lot of new techniques to try to deal with this. So that alone could be an interesting project. Choosing something where you think you need this type of model, where you have a panel data, lagged dependent variable, and then you can throw some of these new techniques, and that would be a cool sort of rabbit hole to potentially go down if you're interested in these types of issues. Finally, we'll mention measurement error, which is obviously can be a big thing if we're mismeasuring, and we know that we're probably mismeasuring some type of variable. So consider a population regression that posits a simpler relationship between earnings and education. So the hypothesis probably being that this is positive. If you have more education, you have more earnings on average. However, education is inherently difficult to measure. We often use years of schooling as a proxy. So we might say schooling, this is years of schooling equals education, but that's noisy, right? Because people can have many years of schooling and be like, oh, I didn't ever actually go to class. So that's going to be an issue in terms of measuring education using schooling. That would be an example of measurement error. That's also a difficult one. It's not like you can necessarily fix that without a sort of a costly thing, like you'd have to have some testing or something. So that might be very costly to get better measurements of education. So if we had this, then we'd have YIT really equals beta schooling with a WIT, where schooling equals this guy. And then, of course, schooling W omega is not equal to zero for the same reasons we've expressed above. So there's a bunch of different reasons. The upshot of all this is there's a bunch of different reasons endogeneity could occur, or we could have a theoretical reason that this is happening. Now, in every single one of these, if you ran OLS and then said, what's the covariance between X and E, the sample errors, you basically get super close to zero every time. The only difference from zero would be rounding errors. And so, again, this is not really testable. I have endogeneity spelled bad at the bottom of this. Sorry. I'm sure there's other typos too. That one I noticed. So let's get into solutions for some of these endogeneity issues. So one big one that happens in economics, but we're not going to go into, is called structural modeling. That essentially amounts to, I'm going to just write down the entire system that I'm trying to estimate and do some type of simultaneous estimation of everything in the system at the same time. So if you were writing down a supply equation and a demand equation and being really explicit, these are different parameters, then you might be able to come up with just, here's my whole theory laid out. Instead of just trying to estimate the demand equation, I'm going to estimate demand and supply simultaneously. And I'm going to input some constraints. Then those constraints are going to help solve the endogeneity issue. Now, the reason we're not going to go super into that in this class is that tends to be, structural modeling comes from expertise about the system itself. So economists who are experts in macroeconomics have a bunch of theoretical equations that they can write down, understand the theoretical endogeneity issues inherent to that system, and simply constrain the system to sort of solve away those endogeneity issues. Now, what we're going to more focus on is, what if you don't have structural modeling and you're still doing what's called reduced form, which is essentially what we're doing in all of this class and what you're doing when you're doing machine learning and stuff. And that's more of a statistics or data side fix to some of these issues. So it's kind of like, I have an endogeneity issue. I want the correct coefficient, but I'm not going to be doing structural modeling where I model the entire system, because that can be unbelievably difficult sometimes, especially if you have a very complicated system underlying your data. That also is going to be a data intensive process, because to the extent you have a larger system of equations, of structural equations going into your system, that's going to require more data to estimate that system. So we're going to mainly talk about what's called instrumental variable estimation, both in its simplest form and more complicated forms. So let's first suppose we have a model in which we have up to k independent variables. So k could be 5, 10, 1, whatever. So that's k is just our number of independent variables, and we'll call those xi. And those are going to be correlated with the error term. So we're going to assume that we have an endogeneity problem off the bat. Suppose further that there exists a set of L variables, so some other number of variables, and we'll call these Zi. These variables are correlated with our independent variables that we're interested in, but are not correlated with epsilon. So if these were our variables, then we would not have an endogeneity problem. But these are not our variables. We're just imagining that these exist. So we're interested in estimating the influence of our independent variables x. We know that we have an endogeneity problem. We've assumed that. But then we're assuming further that there does exist this other set of variables that's correlated with x, but uncorrelated with epsilon. We can't use standard ordinary least squares with x in this case, but we might be able to exploit the exogeneity of our z variables, because they're correlated with x, so that when they move in certain directions, x moves in certain directions, but not with epsilon. So maybe we can use this fact that those are exogenous regressors to help us get the correct answers for x. The set of variables Zi are the instrumental variables, or instruments, and such, and we call this set of variables Z, this L set of variables Z, we call those instruments. Now, an example of an instrument, because I want to tie this back to something you've done in the past, we know that if we use price, like gasoline price, as our dependent variable and gasoline quantity as our independent variable, we will definitely have a simultaneity endogeneity issue, which you've shown in your homework and we showed on the very first lecture. But then I asked you in the homework, come up with what type of data. Well, we showed in the lecture and in the homework, if we only shifted one of the curves, then maybe we could actually get our hands on the correct parameters. So now what we're talking about is maybe we can come up with a variable. Suppose we're trying to estimate the demand curve for gasoline. What if we can come up with a variable that only shifts the supply curve of gasoline? If we were trying to estimate the demand curve, that variable that shifts the supply curve would be correlated with the quantity, right? Because if supply shifts, quantity changes. So they've correlated. But as you already intuitively know, that variable would not be correlated with the air term in the demand equation. So that would be a great theoretical example of an instrumental variable we might use. And that's why we need theory for some of this stuff, because we have to come up with a theoretical reason. I believe that this variable shifts supply, but not demand. Or I believe this variable shifts demand, but not supply. Those are the reason I had you guys thinking about those. Those are the types of variables that we might use as exogenous instrumental variables. You could also think, I mentioned some other examples where some simultaneity shows up, like in predator-prey systems. So maybe there's a lot of endogeneity going on between lion populations and zebra populations. And if you just looked at lion and zebra populations, you're not going to be able to extract the true parameters of the system, because it's a system of equations that determines that. Like zebras eat grass. When there's more grass, there's more zebras. But then when there's more zebras, there's more lions. And where there's more zebras, lions hunt more. And then there's less grass because the lions are helping tamp down the zebra population. Those types of things are going to lead to bias estimates of the fundamental parameters in that system. Now, what if the government changes hunting licenses for zebras all of a sudden? There's a new policy where hunting licenses for zebras got less expensive. That is probably uncorrelated. The lion population doesn't lead to, like, maybe in a longer end sense it does, but that's going to be an exogenous shifter to the parameters of that system. And those are the types of things we might be able to be willing or trying to look for to shift around that system in ways that are outside the system. So that type of reasoning is what we use when we're trying to come up with this L set of variables, ZI. So let's look at the theoretical impact of endogeneity, and that's going to help us understand the usefulness of instrumental variables. So the least squares estimator is going to be biased in the presence of endogeneity, because we're going to have the expected value of B, our estimate, conditional on x equals beta plus x prime x inverse x covariance x epsilon. Normally, we get rid of this whole term because this goes to 0. But now, because that doesn't go to 0, we can't get rid of it, which shows that this does not equal the population parameter. And that's just the mathematical expression of what's happening, which you've seen before. Before, this goes to 0 by assumption, the no endogeneity assumption, basically, that this guy equals 0. But now we're violating that assumption. By assumption, we're violating that assumption. So the least squares estimator is also not consistent. This means that even in the limit, if we collect more and more data, that does not fix this issue. Getting more data does not cause this to get closer to 0, because this is not 0 for a theoretical reason. And we kind of saw that in the very end of the first lecture. I did the big sum simulation, and we got the right parameters, but from a much smaller data set by critically thinking about the endogeneity and simultaneity issue in that example. So inconsistency essentially means that even if we have more data, that's not going to fix this problem. Now, this bias and inconsistency is not limited to just the estimation of the coefficients on the endogenous regressors, because oftentimes we might have a big multiple regression that has some mix of both endogenous and exogenous regressors in it. Now, if we have such a system, then this issue will get biased definitely on our estimates of the parameters of the endogenous regressors, but that will spill over into bias on the coefficients of all of the independent variables in our system. So that's called smearing. It sort of contaminates the entire regression model when we have this issue. Now let's first think about our first fix to this problem is going to be called the instrumental variables estimator. So we assume, of course, we're seeking to estimate just the regular population regression model right here. But we think that some of the variables X are endogenous. So we have covariance X epsilon does not equal 0. Assume we have another set of variables Z with the same number of variables X. So we're going to just assume L is equal to K in this case, but we don't have to hold on to that assumption forever. Z includes the exogenous variables from X plus exogenous instruments. So that, just to be clear, if we have a regression that has both endogenous regressors and exogenous regressors, we always include the exogenous regressors, even if we don't think they're good instruments, in our set of instrumental variables. Plus, we come up with new variables that we think are good stand-ins for our endogenous regressors. So those are the two subsets of variables that live in Z are any variables in our regression that we believe are exogenous, so don't have the issue, plus our stand-ins for X are endogenous regressors, because we're going to come up with a list of variables that we believe are exogenous, correlated with X, but not correlated with the error term. Out of these variables that we called instruments, these extra variables we're finding that we believe are exogenous but correlated with X that we're going to use in stand-ins, we want two characteristics from these. A, they need to be relevant. That's the correlation part. They need to be correlated with X. Because if they're not going to be useful as stand-ins for X. Now, the second thing is they have to be exogenous. They can't be correlated with epsilon. Now, this is obviously a trade-off because X is correlated with epsilon. If something's super, super, super correlated with X, it will also be correlated with epsilon because X is correlated with epsilon. Specifically, if you might be able to find an instrument and say, this is perfectly correlated with X. That's not going to be a good instrument because if it's perfectly correlated with X, then it's also certainly correlated with the population error term and is not actually exogenous. So we need it to be relevant, correlated with X, but not correlated with the error term. So we want to find those special variables that it's like this correlation is coming from the place that's not correlated with the error term. The former is testable. We can check if an instrument is correlated, just literally we could check the correlation. The second one is not really testable. We can only really come up with theoretical reasons that a variable is endogenous or exogenous, as we've already seen a bit. Given we've identified a set of instrumental variables, so let's suppose we found a nice set of variables or one variable, depending on how many we need, that meets these two criteria, relevance and exogeneity. Then the instrumental variable estimator looks like this. So BIV, the instrumental variable estimate, is Z prime X inverse Z prime Y. So we're essentially, remember, this used to be X prime X inverse X prime Y. Well, now Z is playing a role in this too. Basically, this amounts to, what you can show this is doing is it's running a regression of X on Z. So predicting X with Z. If Z is relevant, we should get reasonable predictions of X. And then we're using those predictions of X based on Z in our main model. That's all happening in this math right here. So the reason that that works is because we have relevance. So Z is moving in the same direction of X still, but we've left out that part that's correlated with epsilon by mapping Z onto X, because we know Z is uncorrelated with the epsilon, and only the variation is Z is feeding our variation in X. And therefore, we've netted out the correlation between the error term and X. Now, having this X in here allows us to essentially map that back into the units of X. So we can express our coefficient, and this is still a slope coefficient. How much does Y change when X changes? By including this X in here, we still get that nice interpretation. Now, for a bivariate regression model, we can show that this BIV is now, and it's worth sort of thinking about what's going on here, because now we have the covariance between Z and Y divided by the covariance between Z and X. This is what's netting out. So that correlation between epsilon and X is never allowed to sort of make an appearance in this regression, because that would be inside the covariance of Y and X, which is normally up here. It can be shown that the expected value of the IV is equal to zero, is equal to beta if the relevance and exogeneity assumptions that we mentioned above hold. So that's why we, of course, need those assumptions. Those are what's needed to show that this gets unbiased, because that's what we're looking for, is an unbiased estimate in the presence of endogeneity. And so you could prove that. The IV estimator essentially isolates exogenous variation in X, that variation which is related to Z, and uses that exogenous variation in X to estimate the relationship between X and Y. This is just like saying, if I could only shift supply, then I could just use that shifter to just get the demand curve parameters. This says the same thing as that, but now this is much more general than that argument was. Now, we have many cases where we might set up a big system of equations, like in a supply and demand system or a predator prey system or something like that. And then there's a better method probably is two-stage least squares. So consider the following linear regression system. Or I really have put two different ones here. So you have one that's quantity demanded is price income, quantity supplied, price input, price rainfall, because rainfall maybe is something that influences quantity supplied of agricultural products or something. And then, of course, in equilibrium, we have quantity supplied equals quantity demanded. You use this, a very similar system to this, to show that we get simultaneity, a specific type of endogeneity in this system. This is another one where we might have loans, interest rates, profit for demand, interest loans, and this is like business loans. So a business loan supply would be the interest rate and then the federal funds rate, for example. This is banks giving loans, corporations demanding loans. Similar supply and demand system. Now I'm referring to this system for agricultural commodities in this paragraph. So price is clearly an endogenous variable in both equations, which we've discussed before. That's the example from the first lecture. However, input price and rainfall, we might say, are both plausibly exogenous, because remember, we can't really test this. So we often say plausibly exogenous. That means I can come up with a theoretical argument that rainfall is exogenous to the system. Namely, the quantity supplied and the price, those don't impact rainfall, but rainfall does impact those things. So that would be the argument to say that something is plausibly exogenous. We could apply instrumental variable regression if we chose one of the two exogenous supply shifters as our instrument. And we're also going to assume that income is exogenous. So we're just going to assume that price is the only endogenous variable. So we could do the above, because we only have one endogenous variable. We could do this instrumental variable thing by just choosing one of the exogenous variables, but we have three, right? And so really I'm only assuming income is exogenous, because remember I said in our subset of Z, we have two subsets, all the other exogenous regressors, and then our set of instruments. So in this example, this Z matrix is all our other exogenous regressors, plus two things that we could think could be good stand-ins for price itself, because input price probably affects price. Plausibly, it affects it in a way that's unrelated to quantity supplied or quantity demanded. Rainfall, on the other hand, also plausibly influences quantities and prices in ways that are outside the system. So we're shifting around price with rainfall in an exogenous way. That might help us get our hands on the parameters. Notice rainfall and input price. These two guys are both in the supply equation. So if we're using those as instruments, those are going to be instruments for price in the demand equation, because we're going to remember, shift around. There's a dog barking outside. Sorry, I got freaked out for a second. I was like, it's very early in the morning, so I didn't know what that sound was. So supply, remember, this is going directly back to what we were talking about in the first lecture. We want to shift around supply in order to identify the demand curve. So by shifting around rainfall and input price right here, we're shifting supply around. We have another exogenous regressor in demand, the equation we're trying to estimate. And so Z becomes all of those. Other exogenous regressor, two things that we're exogenously shifting supply around with to trace out the demand curve. So this is coming directly from that intuition we've been developing over these examples. Now, this has too many variables to use this, but we can still use that logic I explained, because fundamentally, we're going to map these two guys to this price, predict price with this set of variables, and then see, okay, can we have that new predicted price be a stand-in for our endogenous price? So two-stage least squares is the name of this method. This provides a method for extracting all of the useful variation, because we'd be leaving some information on the table also if we just chose one, but maybe these are both shifting around supply. It's better if we can get a better estimate of our demand curve if we shift around supply more. So we want to try to use all that information. So two-stage least squares allows us to use all of that information in an instrumental variable type setting. So if Z contains more variables than X, like in this case, input price and rainfall, that's Z, when really income, input price, and rainfall is Z, but price is one variable, X, then Z prime X is not square and is not invertible. So we can't use just that super simple method we mentioned above, but the intuition I just called is the same. So we need a new estimator, extract all of the information from our instruments. Two-stage least squares and similar estimator makes use of the fact that if Z1 and Z2 are both valid instruments, so that could be like input price and rainfall, for some endogenous regressor X1 like price, then any linear combination of them, Z star, Z1 plus a Z2, is also a valid instrument. Relatedly, if each instrument is uncorrelated with epsilon, then any linear combination of instruments is also uncorrelated with epsilon. So the two-stage least squares estimator involves projecting the columns of X into the column space of Z. So this means estimating the values of X using the instruments via OLS regression. So literally, we just run a regression with X as the independent variable on Z, the dependent variables in that first stage regression. We should get reasonable results if the relevance assumption that they're correlated holds. And then using those predicted values of X hat from that first stage regression in the regression of interest in the second stage. So X hat equals Z prime, Z prime Z inverse Z prime X. So that's what X hat equals just in matrix algebra. So this is essentially Z prime Z inverse Z prime X. So that is the beta coefficient, right? That's how we get, that's just the formula for B, OLS. And then if we multiply our coefficient by our variable, then we get a predicted value, X hat, right? So normally we'd have something like normally we'd have something like BOLS is X prime X inverse X prime Y. So without this right here. Now, if we were now just without even thinking about an endogeneity, let's assume we're running X is the dependent variable and Z is the independent variable. Then B for that, B would equal Z prime Z inverse Z prime X. That would just be the coefficient. Now, this is the predicted value, not just the coefficient. So how do I get the predicted value? I multiply the coefficient by the variable, and then that gives me the predicted value. So these are our predicted values, x hat. Now we can take those x hats, put them in our standard equation, x hat prime x inverse x hat prime y to get our two-stage. Why is this an x and not an x prime? For the same reason that this is an x and not a z, because our x hats down here are like our z's. Those are our instruments that we created by predicting values of x off of exogenous shifters. And we can write that out, of course, as all this by substituting away what x hat actually is. So in practice, analysts tend to calculate the first and second stage results. So this is just showing you could do this in one step right here. You could put all your z's and x's in and do this in one step of math. However, what I'm saying in this paragraph is generally we do them separately because we want to assess that first stage regression. What does it R squared look like or F stat look like? If those are super low, then we might be violating the relevance assumption. However, you got to be careful because if those are too high, like in the limit, if R squared is 1, then you're definitely violating the exogeneity assumption. Okay. So let's look at some of this stuff in action. So I have a CSV file here, Texas oil price and production. So we might have an endogeneity issue because if the price is higher, if I'm a Texas wildcatter, I'm like, oh, the oil price is super high. I want to drill more oil. So that makes sense. That's the theory, right? Higher price, higher production. However, what happens to price when oil production is really high? There's a large supply of oil. To sell that oil, I might need to lower my price. So we have basically a reverse causality issue going on that might cause endogeneity. So first, just thinking about what data is in this, there's 3 variables in this just to show what's happening. So this is oil production in Texas. And then 2 different oil prices. I have the WTI price, which is the West Texas Intermediate. That price is actually happening in Oklahoma, but it's very close to Texas. The market for that oil is in Oklahoma. And that's the benchmark oil price for oil in the United States. That is the price that we mainly would expect to be contaminated by production. Lots of production in Texas probably will decrease the West Texas Intermediate oil price. However, Brent oil price, you can see these are correlated. When they're both low, they're both low. When they're both high, they tend to be both higher, but look over here. So maybe not. For the WTI, that might be some of that endogeneity issue. Now, Brent is the European oil price. So that's highly correlated with the US oil price, but much less likely to be impacted by production in Texas alone. Because in Europe, they get a lot of their oil from Russia and the Middle East, for example. So maybe it's plausible, that word plausible coming in, to argue that the production in Texas does not influence the Brent crude oil price the same way that it more plausibly impacts the West Texas price. And it's often about these sort of trade-offs. So even if they're both endogenous, Brent is likely to be less endogenous. So we could compare the results, for example, and say, well, is one changing at least? Is one bigger? Is one smaller? That might help point us in the direction of the bias at least. So I'm going to just define my dependent variable as production. Endogenous independent variable is WTI price, the West Texas price. And then I just made an argument that maybe a good instrumental variable is the Brent crude oil price. So now I'm just adding ones because we're going to have a intercept in this regression. And now, before, a lot of places I use packages to run regressions, but I want you guys to know that we can do all of these regressions using matrix algebra in Python. So the OLS coefficient or sorry, I'm just going to do, this is just X prime X basically. So that's X, NP dot is matrix multiplication, X transpose times X. So this is X prime X right here for OLS. And then of course, also in our OLS, we have X prime Y. Those are just components of our equation for the BOLS sample estimate. Now BOLS right here, this is X prime X inverse, right? Or this is just X prime X. So then this is X prime X inverse. And then this is X prime Y. So that's BOLS, right? That's just our equation from BOLS, X prime X inverse, X prime Y. So those are our OLS coefficients. And now we can get predicted values from our OLS. That's going to be predicted production. So then we can get residuals and standard errors. Because I'm doing this with matrix algebra, I just have to extract all of the errors and stuff. So I get my predicted values. Then I take my residuals or my actual value minus my predicted value right here. So I'm just creating my sample error terms. And then I can get my sigma squared after I have my sample error terms. So that's the variance of the residuals, right? And then I can get my OLS standard errors. So sigma squared OLS, X prime X. You could probably remember that from the variance from OLS. This is our standard errors for our OLS B estimates. And then, of course, once we have a standard error, we can get a test statistic, which is just our OLS coefficients divided by their standard errors. So that's always what a test statistic is it is an estimate divided by its standard error, right? So we're just getting degrees of freedom here to do hypothesis testing, as you may or may not remember from a past life. Look it up. So this is all just essentially basic hypothesis testing, what I'm doing through here. Let me know if you have any questions about it. I'm happy to walk you through that. If you threw this in Chat GPT or something, it would be like, yes, this is hypothesis testing, and it could explain it to you. That might be a little bit review, because it's possible you haven't had to think about hypothesis testing too much recently. But this is sort of a good, this part of this is a good, because we haven't done the instrumental variable stuff yet. So then we can just look at our OLS results right here. We don't know if they're good or not yet, because we don't remember this. Now we're looking at observational data, so it's not obvious that we have an endogeneity problem. So all we can really do now is say, okay, our intercept is 143,500 barrels of oil production approximately. And then the price, we have this big positive parameter. So when WTI price goes up by $1, production goes up by about 195 barrels on average in this sample. Okay, now that is the true correlation. That's the true slope in the sample, like explicitly. However, the question is that the true effect of WTI price on production? That part isn't clear yet, because production could have this feedback effect. And it's worth understanding the differences. That's the true slope in the data, but it may not be the true effect of WTI price on production. Make sure you understand the difference in those two things. Now, there may be an endogeneity issue here for exactly the reasons I mentioned above, looking at the scatter plot, talking about Europe versus US, Texas production. So let's try using European oil price as an instrument. So now we're just going to, here's our Z, we're adding ones to it. Now we can just do Z prime X, because this is from, let's go find our equation again real quick. We're going to just do this equation. We've done X prime X inverse X prime Y and looked at those results. Now we're going to do Z prime inverse Z prime Y. Z prime X inverse Z prime Y to compare what happens if we use an instrumental variable instead of the potentially endogenous regressor. So here we're just getting that ready. Same thing we did above with X. Whoa. And then we have BIV, of course, is just these two guys. So very similar math to what I was doing above, but now we're using Z as a stand-in for X. But of course, X is here to get us our nice interpretations still. Predicted values, Y minus Y prediction. Now we have different, because we have different error terms because we're going to have a different coefficient now. We're going to have more bigger error terms because we're no longer minimizing the sum of squared errors. So they have to be bigger relative to X, right? That's okay. We're explicitly not minimizing our squared error terms, but we're doing that for the right reasons. So I will want you constantly thinking about those trade-offs in this class. Those are the trade-offs that people who never take classes like this never think about. And so that's fundamental right there. Those types of trade-offs, several of which I've mentioned in this particular lecture. So same stuff, getting the standard errors like before. Now, this isn't obviously the right way to get standard errors for all these things, which I'll have you guys think about in the homework. I think this homework may be the next one, but you'll have to think about standard errors in the context of endogeneity soon. So that's exciting. So now we're just getting sort of test statistics here, blah, 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 same stuff. Now let's look. Okay, now we have a much bigger coefficient, way bigger. So now our intercept, our effect is so much bigger that the intercept is a negative now, which honestly makes sense. If the price is 0, I would negatively produce if I could. That's not a real choice. So the actual predicted value would probably be 0, but maybe pumping oil back in the ground to store it does count as a negative production. Worth thinking about. Is storage negative production? I used to be a energy storage analyst, so these are the nerdy things I think about. But look, that's a massive difference by using this coefficient. So is this a good coefficient? Hard to say. This is not a very robust model. It's just simple regression, but definitely evidence that this is an issue right here, right? That we're underestimating the influence of price on production, because by using this plausible instrument, I mean, these appear to be correlated. Certainly, maybe production in Texas does impact the Brent price, but certainly it doesn't impact it as much as it impacts the Texas price. So the dramatic differences in these two coefficients are telling us something. Now, let's try just doing two stage least squares. So we don't have extra coefficients. We're just doing Brent on this, but I wanted to show you what it looks like if we do two stage instead. I think you can work through this math fine. It's basically doing a bunch of regressions. And then we get down here. So the first stage results, now we can look, okay, instrument 1. And this is actually a little bit concerning because of this, or sorry, this is a standard error. So this is the coefficient. Okay. Yeah, so right here, these two sort of results are a little bit concerning as we don't have a very strong relevance. So that is probably a very noisy estimate that we saw above. So by just doing instrumental variables and not two stage least squares and not explicitly looking at this, we probably have a relevance problem here because we see that we have a very low R squared. So there isn't that much correlation as maybe we would have expected between WTI price and Brent crude oil price. Not only that, but this is not a significant, this p-value is 0.3, so that's not even a significant coefficient. So here's just that coefficient again, and we have our standard error. Now that's super significant, so that's a little bit scary, right? So in our first stage, we don't have significance, but in our second stage, we have very strong significance. So these are the sort of issues we would probably want to assess after the fact. We have what's called a weak instrument, we'd say, because of the low correlation between WTI. So now we know that the pandemic caused crazy variation in oil prices. The pandemic caused oil prices to crash. So we can, and this is what we start doing now. We say we have a weak instrument. We need a better first stage model. Maybe we can get a higher R squared if we think of other instrumental variables that we could put into that first stage regression. So now all I'm doing is adding a variable called pandemic, which is a dummy variable, 0 or 1 categorical variable, but like whether pandemic is happening. And so let's just reassess now. Okay, this is now Brent is less significant than it was before, but this is very significant. And look at our R squared is actually pretty sweet now. Because we don't, again, like having too big of an R squared would be bad in this case. Honestly, getting much closer, higher than that, I would begin to be worried about the other assumption, exogeneity. Now, pandemic, you can probably argue is it's hard to imagine how oil production leads to a pandemic. But it's not only that, there's more complicated ways that endogeneity could show up, like pandemic affects this other variable over here, which is very endogenous or something like that. Well, let's take a look. Okay, now not as extreme, but still much bigger than our original coefficient. So now things are getting maybe a little bit more stable, and we're like, yeah, that other one was huge and we had a weak instrument, but it was bigger. So that made us be like, it's a lot bigger. So now we have a better first stage with a nicer fit, but probably not such a big fit that we should be worried about exogeneity. And now we get what appears to be a pretty reasonable coefficient. It's closer to that first one, not totally insanely bigger. We have a stronger first stage, and we see, yes, indeed, this is bigger. Now, theoretically, we would expect a bigger coefficient if we think through it, because ultimately the issue would be higher price causes more production causes lower price. That will ultimately lead us to underestimate the influence of price on production. Think it through if that's not clear. And so that sort of theoretical reasoning needs to be happening here because this is consistent with that, but it's not so crazy that it's 20 times bigger or something. All right. So this is now how we fix endogeneity issues. Tons of great stuff for a project here. If you're interested in this stuff, the way to do a project like this is come up with a model you would be interested in estimating, come up with a reason that you think at least one of your variables is endogenous, come up with a set of one or more instrumental variables that you might fix that issue with. Because just going through these coefficients like I've done in this lecture would be a great project. Look, I get one, I don't know if it's wrong or not, but then I try something else and I get a way different one, but I have some other issues with that one. Okay, let's complete the trade-offs, complete the circle to get the right answer here. And then we end up with something that looks very reasonable, is in between the two extreme cases. Okay. Like that would be a great story of a project. Please don't hesitate to reach out to me. A few students I've met with several times already about their projects. So please don't hesitate to reach out to me to chat about your project. All right. And also, of course, don't hesitate to reach out with questions about this or any of the other lectures, homeworks, quizzes. Okay. Thanks.